Okay, we want to do another example. And in this case, what we're going to do is we are going to classify the pink grain size curve. And what do I mean by that? That is, on this chart here, we have the pink curve, and this is the pink curve right here. So what's given is that curve, and we are also given this pink information that the fines have a liquid limit of 42, a plastic limit of 20, which gives us a plasticity index of 22. So let's look at this curve, and what do we get from it? Well, the first thing that we can get out of it is how much sand, how much gravel, how much fines do I have? How do I get that? Well, the boundary between the gravel and the sand is the 4 sieve, number 4 sieve, and the boundary between the sand and the fines is the number 200 sieve. And so I look at those, and I look at my curve where they intersect. So the number 4 sieve, number 4 sieve hits the curve there. The number 200 curve, number 200 sieve hits the curve there. And what is that? How do I read that? Well, the way I read it is that for the 4 sieve, I come down here and then I read off that that's at 69%, which means I have 31% gravel. In other words, anything above the number 4 sieve is my gravel. That's 31%. So I have 31% gravel, and then how do I get the amount of sand? Well, this amount of sand is what? It's between the number 200 and the number 4, and that gives me, that distance there is 63% sand. So I've been able to get from the curve how much sand, how much gravel, and then what do I have? I have 6% fines because it hits here at 6%. So from this curve, I can read my percent sand, my percent gravel, my percent fines. And at this point, we can see that, well, we've got a sand because it's 63% sand. So I know that if I'm doing everything right, I've got a sand. The other thing that I want to get from this curve is what we call the D60, D30, and D10. What are those? Capital D60, capital D30, capital D10. How do I read those off from this curve? Well, by definition, they are the D60. I start at 60%, I hit the curve, I come down, I read that value. 30, come down, read that value. 10, come down, I read that value. So my goal is to read the grain size, and remember the x-axis down at the bottom is grain size in millimeters. At the top it's the sieve numbers. At the bottom it's the grain size. So remember there are 2 x-axes. So let's just make a point of what is this bottom x-axis. Well, the x-axis on the bottom is a log plot, and as you know, a log plot has no 0 on it, and that a log plot at evenly spaced increments differs by a factor of 10. So now this log plot, in addition, is a little bit unusual in that the big numbers are to the left and the small numbers are to the right. So it's going in a sense backward, but this is the way most people plot it. So we have, so let's look at it, put it this way. So small numbers here, so I've got 0.01 at the far right, then 0.001, let's do that again. 0.001 at the far right, 0.01 there. That's a factor of 10. And then another factor of 10, 0.1. All of this is evenly, you can see that's evenly spaced. That space is the same as that space. Then another factor of 10, 1. Again, that's evenly spaced. Another factor of 10 takes me to 10, evenly spaced. Another factor of 10 takes me to 100, evenly spaced. So I have, in this particular case, I have 5 evenly spaced cycles on our log plot, and they all vary by a factor of 10. That I need to keep in mind when I read my plot, because it can be confusing in reading this thing. So when I read my D60, there's my 60, I come down, I have to read this value. Well, that value is what? Well, that's 1, that's 10, so my number is between 1 and 10. And if I look at it, and this is all approximate, you get about 3. So I get a D60 of approximately 3 millimeters. Then I do the D30, same thing. I come across at 30%, I go down, I read the number there. Well, it's going to be between 0.1 and 1. It's close to 0.5, but it's a little bit less than 0.5, so I get D30 of approximately 0.45 millimeters. And then I do the same thing. I read off D10. Again, it's between 0.1 and 1. It's less than 0.5. It's approximately 0.2. So I get a value of approximately 0.2 for my D10. There are 2 other terms that we define for the purpose of soil classification. Again, these are just definitions. CU, C sub U, and C sub C. And what are they? Well, CU is D60 over D10. And so D60 over D10, that's my CU. I get a value of 15. My CC, my CC is D30 squared, and I divide by the other two, D60, D10. So C sub C is D30 squared divided by D60, D10, and I end up with a value of 0.3375. So the 2 numbers I need to remember there, I've got a CU of 15, I've got a CC of 0.3375. Let's see if we can remember those when we take them. And then I have my, given what I need, well, I need my liquid limit of 42 and a plasticity index of 22, so 42, 22 for those 2. So let's take, okay. So maybe I'll just write those down. So I have a, we end up with CU equals 15 and a CC equals 0.3375, and then we have the liquid limit is 42 and my plasticity index is 20. And this all comes from, that's from the grain size curve, and that's given information. So we take that information and we go into our plot, or our chart, and, 42 PI was 22, 42, 22. I made a mistake there. So let me just correct it. It's 42, 22. So let's go into our plot here. We are, I'm going to have to magnify it. We know we have a sand, put it this way. So we can start at the sand. And again, we know we have a coarse grain soil and percent sand's greater than percent gravel, so it's a sand. Then what do? Well, I judge by how much passes the number 200 sieve. Well, we had, if you look at the back of the grain size curve, we had 6% passing the number 200 sieve. First, so what is that? Is it less than 5%? No, it's not less than 5%. Is it greater than 12%? No, it's not greater than 12%. Is it between 5 and 12%? Yes, we had 6%, which is between 5 and 12%, so we are in here. Then we have to decide, do I go up? Do I go down here? Well, if I look real closely at this, is my CU greater than 6 or is my CU less than 6? Well, my CU is greater than 6, so that takes me up here. So I've come in this way, and then I have to look at my CC. And is my CC, well, this is my CC between 1 and 3, or is my CC not between 1 and 3? Well, our CC was 0.3375, so it was not between 1 and 3, so I'm down here. Then I have to look at do I have MLMH or CLML or CLML? Okay, so what do my fines plot as? Well, to figure out what my fines plot as, I have to go down below here, and we had 42.22, so 42 on the x-axis for the liquid limit, 22 for the y-axis for my plasticity index. It plots in there, which is CL. So my fines plot as CL. So when I'm going across, so in other words, I started at the sand, I go this way, then I had my CU bigger than 6, then my CC was not between 1 and 3, then I have a CL rather than ML or MH. So I'm down here, so that takes me over to here. I have an SPSC. So my soil is SPSC, and then how much gravel I had 31% gravel, so I had greater than 15% gravel, so I'm here, which means that I have SPSC, and then I read this poorly graded sand with clay and gravel. That is my answer. So SPSC, poorly graded sand with clay and gravel. And that is my answer here. So if I look at this, poorly graded sand with clay and gravel, SPSC. So that's as hard as they get. If you can do that one, you can do any of them. So that's, if you know all those little details, you'll get that one. You'll get all these basically. Now let me give another example of a fine-grained soil, and how do I know? Here's my given information. So I have this is my given information here, and you can see that I have what? In my pan, I have 70%. In my pan, I've got 70%. So I have 70% fines. Well, that's a fine-grained soil. So in addition, that all adds up to 30%, which means I have 30% sand. So what I need to do is I need to plot my liquid limit and my plasticity index. So my liquid limit is 38. My liquid limit is 38. My plastic limit is 18. That means my PI is 20. So I have to plot 3820. So I'm going to plot 3820 on the graph. And what do I have here? So I've got, so I come down here, and I'm at 3820. 3820 is going to be in here, so it's going to be a CL again. So when I go now, then I have to use this. This is the fine-grained soil classification chart. This is much easier to use. And what do? I come in, and once I've determined I have a CL, well, I don't have to go through all of this. I can just start. I've got a CL. because it plotted as CL. So I start here, and then I have to look at the, do I have greater than or equal to 70% passing the number 200? Yes, I do. I had equal to 70%. So I am, I start here, I'm here, and then, I go across here. Then it's, 70 to 84% passes the number 200, so I'm in there. And then I have, is the percent sand greater than percent gravel? Yes, the percent sand was greater because I had no gravel. And so I end up with lean clay with sand. So my final answer is CL, lean clay with sand. And CL, lean clay with sand, that's my answer. So that is how we classify soils. And if you can do these problems the ones that I went through, and I'll send you some more, then you are capable of classifying a soil. So it takes some practice, but everybody gets it. So it's not difficult. Okay, I want to skip that. Before we go on to the next topic, I just want to touch on something that we saw in the lab and give it a little more description. And that is when we liquefied some soils in the lab, I want to describe what was going on there. And if you notice how we did this, we took the sand in our graduated cylinder, and it was saturated with water. And what we did was we tilted the graduated cylinder and and then tilted it, and then we put it back down on the table very gently and let the soil particles float down in the water. And as they floated down, they created a very loose structure, what we call a loose structure. And I'm sort of illustrating that loose structure with this diagram, meaning that if you looked at it closely under a microscope, you might see something that looks a little bit like this, with these particles sort of creating what I would call a card house. Just, in a sense, barely touching each other, touching gently. Now, in other words, we had an ordinary sand, but we created a very loose structure with that sand. Now, what happened when we tapped the side of that graduated cylinder was that, as you would expect for a card house, if you tap a card house, what does it want to do? It wants to collapse. Except that when you build a card house in air and you touch it, it collapses. But if you build a card house underwater and you touch that card house, well, it will collapse, but the cards will sort of float for an instant. So in other words, when we tapped it, the particles floated for an instant. They lost touch with one another, and they're floating like this in a matrix for not very long, but for, a second or so. And so the particles are not touching, and that means the soil as a whole has no strength. And then after a second or two, the particles formed a structure that more looks like that, in a more dense packing. Now, you saw what happened when the particles, for only a second maybe, but long enough, what happened was when the particles were in that form of not touching, they had no strength, and what occurred was that the little simulated pile that we had, went down, sunk pretty rapidly, And that is the process of the soil liquefying. That's how the soil liquefies. I want to describe what I will show you in a video later is sometimes nature creates this card house structure. Or sometimes people do, sometimes nature does. But if we accidentally create this, or if nature has created this, then we have a problem if we have an earthquake. Because that means that we can get this happening during the earthquake. And if that happens during the earthquake, then we can have considerable deformations taking place in our structures that are built over that kind of soil. And let me give you this little example down here. Suppose I have four steps here. I've got 1, 2, 3, 4 of this soil, which consists of the soil profile. I have my loose sand. Well, my loose sand looks like that. It's got that kind of structure. That's what I mean by loose sand. It looks like that. I have a clay layer over the top of it. And I have the soil saturated. That's the meaning of that little triangle there. That means that's where the water table is, and everything below the water table is saturated. So I have this loose sand with water in the voids because the soil's saturated. And I've got my card house structure. So there's my card house structure of my soil. And then what can happen is that I have an earthquake which shakes it. So there's my earthquake. And what happens is it shakes it, and then it transitions, the soil transitions, starts out in my loose card house structure. It goes through the earthquake, for instance, and settles down like that. Well, what happens when that occurs? I get my soil layer, the denser sand, settles down, and I can get the situation where I basically have a water layer there, because I got sand here, but I get plain water, not particularly clean, but water up above it. This is unstable because I have clay here, I've got water, and then I've got sand. So what's going to happen to that water? Well, what can happen to that water is that it makes this clay floating on the water, doesn't work very well. So my clay layer then begins to break up, and I get cracks in the clay. See those cracks there? And what can occur is that these clay blocks, well, what do they want to do? They want to sink downward. They sink down into that water layer because it's unstable situation. If they sink down into the water layer, then where does the water go? Well, it comes out. Squirting out. Okay. And this has been seen many times in an earthquake. And I will show you a video of it later. So anyway, this little demonstration that we did in the lab it sounds a little bit odd, but it has a lot of practical implications, and that can cause major problems in an earthquake. Okay, we'll stop there.